Hi, welcome to another EC&M Tech Talks. Today, motor installation. So we're going to talk about everything from the disconnect for short circuit and ground fault protection, sizing the conductors, fuses, motor circuit protectors. We're going to talk about the controller, which we often call the starter. And we're going to talk about the motor itself. So how do we get from point A up here to get power down to our motor? Whether we're installing a new motor or replacing a current motor, we need to take a look at the National Electrical Code. Article 430 is on motors and motor controllers and disconnects and everything we need to know about installing motors. And well, pretty much so. It's going to refer us back to other areas as well. Now, what's nice about as we go through today and we look at these different sections, it's not rocket science. It's in the book already. If you go back to the Informative Annex D as in Delta, Annex D is on examples, and D8 is specifically on motors. In fact, it gives an example for 3 different motors, 2 30 horsepower motors or a single 25 horsepower motor. So, for this Tech Talk, for the purposes of this Tech Talk, this is now a 25 horsepower 3-phase motor. In reality, it's a 3-phase 1/8 horsepower motor. But for today, we're going to use it as a 25 horsepower motor and talk about how we're going to get power to this motor, protect our conductors and the motors as well then. So let's first start with 430.6. Now 430.6 in the NEC talks about the ampacity of the conductors. How am I going to size the conductors to this motor? And that might be the first thing that I want to do. You might say, well, let's look at the nameplate. If we look at the nameplate for this motor, it says it's a 460 volt, 3-phase squirrel cage induction motor. It's rated at 25 horsepower, and it has a full load amps of 32 amps. It's a design B with a service factor of 1.15. So let's talk about what all of that means. First of all, 460 volt, 3-phase motor designed to operate on a 480 volt distribution system then. Induction type motor, one of the most common 3-phase motor that we have out there certainly. Squirrel cage indicates the construction of the rotor, and induction squirrel cage motors then. Now, it's rated for 25 horsepower at 32 amps. For sizing the ampacity of the conductors, 430.6 says it's not a 32 amp motor anymore. It says we have to go to the table, and that is table 430.250 we're going to look at. Table 430.250 is for full load currents for 3-phase AC motors. You see, when it comes to sizing motors, different manufacturers, different horsepowers, different efficiencies, we're going to find different current ratings on the nameplate. When it comes to sizing the conductors, the short circuit, ground fault protection, and so forth, we want to make sure that we're following the maximum value really that we would expect to see on any given nameplate for a certain horsepower motor. So we're going to stick with what the table tells us, which is exactly what the code tells us. And according to table 430.250, full load current for 3-phase AC motors, and by the way, I'm of course as always using the most current edition of the NEC. This is the 2023 edition that we're talking about today. And table 430.250 says that this motor, 25 horsepower motor, no matter what it says on the nameplate, it says it is a 34 amp motor. So if I look at table 250 and go down to 25 horsepower on the left-hand column and read across to where that intersects with the 460 volts, I find 34 amps. So this is a 34 amp motor. In fact, you'll find the reference to the table in 430.6A1, okay? Table values. It says, other than for motors built for low speeds, which is less than 1200 RPM it says, or for high torque motors and for multi-speed motors, the values in the tables are to be used. So there's a table in the back of 250, 250.47, 48, 49, 50, that covers single phase, polyphase, 2-phase, and 3-phase and DC motor. So we use those tables then. And it says specifically in 430.6A1 the 3 items that we're to use that 34 amps for from the table. It says the ampacity of the conductors, which we're going to do, the current ratings of the switches, and the current rating of the branch circuit, short circuit, and ground fault protection. So if we were to look, let's say that we're using, in this case, we're going to use THW conductors to supply this motor. So right away we know THW, if we go to table 310.16, which is our ampacity table, that ampacity table we're going to go down to 75 degree C column, because that's where we'll find THW. T, thermoplastic, H, only one H, so it's rated for 75 degrees C, and the W indicates it's suitable for a wet location. So anyway, THW insulation on my conductor. I go down that column and I'm going to find a number 10 wire. A 10 AWG will carry 35 amps of current flow, which you would say, well, that would be sufficient then. So we could use a number 10 wire. Yeah, we better look a little further into Article 430 then. So now let's go to 430.22. 430.22 talks about single motor applications. And it says conductors that supply a single motor used in a continuous duty application shall have an ampacity not less than 125% of the full load current. The full load current on the motor is not the nameplate, right? We just learned it's the table. So it's 125% of that 34 amps. 125% of 34 amps is just under, what, about 42.5, almost 43 amps. So we could say, well, we need to be able to safely carry 43 amps of current in our conductor. So we're actually going to find that that is 8 AWG THW. 8 AWG, number 8, okay, THW, has an ampacity of 50 amps. So certainly that would cover us for our needed 42, 43 amps. Now, keep in mind, we still have to adjust for the number of conductors in the raceway, and we have to correct for ambient temperatures as well. So we've got to keep that in mind. We're not going to do that today, but we certainly have to consider that. Also, something else, voltage drop. Voltage drop is not a requirement of the code, is it really? It's an informational note. It says we can't have more than 3% on the feeder or 5% from the feeder out to where we, more than 3% on the feeder or the branch circuit, or we can't have more than 5% voltage drop from the feeder source out to where we utilize the power. And the reason for that is, as I say, it's an informational note, it's not a requirement. This is a 460 volt motor designed for operation on a 480 volt system. Okay? Why would the manufacturer do that? They know we're going to have voltage drop in the system, don't we? So they know we're already going to have some voltage drop, so they've rated the motor, for whatever reason, it's the NEMA MG1 standard, for 460 volts. We have to make sure that we don't operate that motor outside of its plus or minus voltage specifications. If we do, that could become the code violation for us. So anyway, we always have to pay attention to voltage drop when it comes to sizing our conductors as well. We've sized the conductors. We say we're going to run some number 8 THW. We're going to go from the fuse disconnect. So we have a fuse disconnect switch. We're going to go to a motor circuit protector. From there, we're going to go to the motor starter, and from there to the motor. Couple of items. Back in Article 430, what is it, 100, 102 on the disconnect? Yeah, 430.102 on the location of the disconnect. This disconnect, well, first of all, it says back in 430.102, we need a disconnect for the motor and we need a disconnect for the controller. However, it also says that if we meet certain requirements, which we're typically going to meet, we can use one disconnect switch for both the controller and the motor itself. So we'll do that. This disconnect switch, according to 430.102, must be in sight of the motor and the controller then. If I look back in Article 100, it gives me the definition for within sight or in sight from. And it tells me it has to be visible from the controller and the motor, as well as it has to be within 50 feet. So I have to meet those requirements. Now, Having said that, there are exceptions, right? Exceptions to plenty of the rules. So as we go through today, we're talking about, as usual, we're talking about the general rules for these installation applications. I should also mention we talked about, we said if this was a continuous duty motor, it had a requirement to size the conductors at 125% of the full load current based in the table. What's a continuous duty motor? There's a definition in Article 100 for continuous load. Continuous load, 3 hours or more at full load. Continuous duty application, continuous duty motors, most three-phase motors are going to be continuous duty motors, meaning the bearings and fans and so forth are sized for continuous operation. The NEMA MG1 standard, though, is where we'll find the definition for continuous duty motors. Basically, if my motor doesn't say it's rated for some type of intermittent duty, 5-minute or whatever, then it's a continuous duty motor. So we size our conductors 125% of the full load current. So for the short circuit and ground fault protection then, to feed our motor and its circuitry, we're going to rely on 430.52, it looks like. 430.52. If we take a look at 430.52, it's the maximum rating for the short circuit and ground fault protection for our motor. So 430.52. A couple of things it tells me in 430.52. First thing it says is that my overcurrent protection has to be big enough to carry the current of the motor. Okay, we understand that. Sometimes I wonder, did we really need to put that in there? But anyway, good idea, I suppose, all righty? And then the next thing it says, the motor branch circuit, short circuit, and ground fault protection, which is what? Fuses and circuit breakers. Right away, I think Article 240. So we're going to have to take a look back at Article 240. And it says, shall be capable of carrying the starting current. And then it goes on and tells me what rating sizes I'm going to need for that protection. And it gets pretty involved. It's a couple of pages long, but there's a table is the key. The table is table 430.52C1. So table 430.52C1. Maximum rating or setting of motor, branch, circuit, short circuit, and ground fault protection. And down the left-hand column, it tells me the type motor that I could have. And so we already said we have a design B motor. So we have a design B motor. So if I go down the left-hand column of that table, and I find there's other than design B, then there's design B, energy efficient, premium efficiency. And I find design B, then it starts to read across, and there are 4 columns. Each one of those columns identifies what type of short circuit and ground fault protection I'm going to use. In the first column, it says if I'm using a non-time delay fuse. If I'm using a non-time delay fuse, then I would take 300% of that table value of 34 amps and come up with the size for my fuses. We're going to use a dual element time delay fuse. The advantage of the dual element time delay fuse is it allows the inrush current to flow into the motor to start the motor, and then as that inrush current dies off, it allows the fuse stays in the circuit to protect the motor. So most often we're probably going to use a dual element time delay type fuse. It says for a dual element time delay type fuse, it's 175% of the full load current of the table. If I were using an instantaneous trip circuit breaker, it's 1100%. And if I were using an inverse time circuit breaker, it would be 250% of that full load current value. So anyway, we're going to go through and size the time delay fuses. So if I have time delay fuses that I'm using, so I take 175% of that 34 amps, which comes out to be 59.5 amps. Well, I go to 240.6, and I can't go to the fuse store, right, and buy a 59.5 amp fuse. However, Article 240 allows me to go to the next higher size fuse in this application, which would be a 60 amp fuse. So I'm going to use 60 amp fuses, time delay fuses, for short circuit and ground fault protection. So what have I done? I've protected my conductors at this point. I haven't really protected the motor yet. For protecting the motor from overload situations, we need to look at the nameplate of the motor. And that's going to be covered in 430.32. So if we take a look at 430.32, and let's talk about overload protection on the motor. Now, this particular motor we said on the nameplate had a service factor of 1.15. What that means is I can overload this motor by 15% as long as I don't exceed any of the temperature limitations on the motor. Where might I use an application like that? Oh, I don't know. Maybe this motor's located outdoors pumping some oil in an application, hydraulic oil or something like that, and the oil is kind of cold and kind of thick. So I have to overload the motor for a short period of time until I get that oil circulating and heated up. I'm allowed to do that with this motor. I can overload it by 15% of its rated value, 15% of its rated horsepower of 25 horsepower. I just want to make sure I operate it within specifications. So 430.32 is where we were headed, and 430.32 falls within Part 3, which is overload protection. And 430.32 is for continuous duty motors. For more than 1 horsepower is A, and then it talks about in A1 separate overload devices. And it gives me not really a table, but it lists 3 separate items there based on my service factor of my motor. And it says motors with a marked service factor 1.15 or greater, which is our motor, the overload protection shall be at 125% maximum then. 125% maximum of what? This is for motor protection, not the conductors. So we're going to look at the nameplate when it comes to overload. We're now going to go back to that 32 amps on the nameplate, and we're going to take 125% of that 32 amps. And that's going to round off to 40 amps, 1.25 times 32. So we're going to select our overload size heaters, as we'd call them, our thermal heaters in the bottom of this starter for 40 amps. As far as the size of the starter itself, our NEMA starters are rated in horsepower. So the code tells us that it has to be large enough to handle a 25 horsepower motor. Right on the nameplate, it'll tell us that a NEMA 2 motor starter, which is a combination of the contacts that open and close to start and stop the motor, and the overload protection would be an entire starter. It tells us a NEMA 2 would be big enough to handle a 25 horsepower motor. Some other items we could cover as well. Sizing, for instance, if we run a wire type equipment grounding conductor. If we were to run a wire type equipment grounding conductor, we'd go to table 250.122 back in grounding and bonding. 250.122 tells me minimum size equipment grounding conductor I need based on the size of my overcurrent protection ahead in my circuit. So if I'm using a 60 amp fuse, it tells me my minimum size equipment grounding conductor is a 10 AWG, a number 10. So I'm running 3 number 8s and a number 10 in this circuit to supply my motor. As far as conduits, I would size my conduits. I'd have to go back into the particular type of conduit I'm using, such as rigid conduit would be very common. And I would find that, well, maybe I could use 3/4 inch conduit. I could sneak by, but I might just run 1 inch to give myself a little extra space above that 40% max fill on that conduit. As far as the type enclosure itself for my short circuit ground fault protection, this is a NEMA 1 enclosure. Table 110.28 gives me all of my different enclosure characteristics based on the number of the enclosure. All of my enclosures protect against incidental contact. When the door is closed, I can't touch any live parts, can I? Also, the NEMA 1 enclosure protects against falling dirt. If you need more protection, consult 110.28. Well, that's the very basics of installing a motor. We've looked at the sizing of the conductors, the sizing of the short circuit ground fault protection. We've looked at the motor controller size and some of its characteristics. We've looked at the overload protection down here at the bottom. Sizing the overload is based on the nameplate data from the motor. Sizing our conductors, the ampacity value, and the short circuit ground fault protection is based on the table values. Having said all of that, that doesn't even hardly scratch the surface when it comes to installing motors. You have to begin and look at the type of motor, the application, the installation you're using. Are you going into a hazardous classified location? All of those type things. So plenty of more information in the code book. You start with motor installation by looking at Article 430. Jump into Article 430. Remember that Annex D8 at the back can help you quite a bit when it comes to getting through everything we talked about today. And in the meantime, work safely.